Great. All right. So Qiskit primitives we're getting to a little bit more of the bookkeeping specific to Qiskit code aspects of how we run these things. Um, it's a little less exciting maybe than other concepts, but I think having a basic understanding of what these Qiskit primitives are and how they operate will alleviate a lot of pain points for people. I think a lot of people look at estimators and samplers, and if you're not really comfortable with what they're actually measuring or what they're doing, it can be really difficult and daunting, and you don't understand why this tutorial you're following is using an estimator, why this one's using a sampler. You don't know what the output from what you're doing should look like. So us taking a little bit to turn away from the circuits and gates and algorithms and things to talk about some of the nitty-gritty of how do we actually do work in Qiskit is useful. That way we can better, that way we're not stymied by trying to understand what our algorithm's actually doing. So what are primitives? They're abstractions for the quantum computation. They are an aspect of how we're communicating our abstract quantum circuit to the actual hardware. You'll see that a lot of older code has different methods for interacting with this, but the primitives of estimator v2 and sampler v2 have replaced those older methods. Now, at the most basic level, when you measure with a sampler, you're going to get a bit string. For each shot, you're going to get some combination of zeros and ones that each qubit collapsed to when you measured it. And you'll do your shots, and you'll have what we call quasi-probabilities. That is that, qubit 0 collapsed to 0 on half the shots and to 1 on half the shots. And so we have the counts of how many times we got each bit string. Whenever we have those bar graphs, that's what that is. That's a sampler primitive. Estimator is going to give you an expectation value of the observable. We haven't covered too much of the linear algebra, but if you take a vector times a matrix times a vector, you end up with a scalar, one single value. And that's the expectation values that we're going to get out of an estimator. So they have some different purposes and some different capabilities. But by using these primitives, it handles a lot of the translation and error mitigation, the batching and things like that. So they're really very helpful. So we're going to take a little bit of time to understand the difference between the sampler and the estimator and how to use them. Okay, the sampler primitive. This is, at the basic level, what we're expecting whenever we measure a quantum circuit. We have our qubits, we're going to measure them and expect them to form a string of, zeros and ones after the measurement. So we're going to pass it a circuit, and we're going to get an output of the counts of each bit string from our quantum circuit. If we have a 2-qubit circuit, we measure it, we get 0 on qubit 0, 1 on qubit 1. The next time we get 0 on both. The next time we get 1 on both, And so we'll get the counts of, for each shot, what the bit string was that came out. It's used a lot for variational algorithms, such as QAOA and VQE. We'll be getting into that early next week. And it handles the measurement errors implicitly. Now, sampler gives these raw distributions, whereas the estimator is going to calculate that vector times a matrix times a vector. That is, that you get one scalar output from the estimator. All right, so as an example here, I have my sampler, and I'm running on a simulator. I define a quantum circuit, all right, and I place qubit 0 in superposition. I do a controlled X to the qubit 1 and to qubit 2. So they are now linked, that if qubit 0 is 0, they will also not flip. But if qubit 1 is, or if qubit 0 is 1, they'll all flip. All right, so I do my Hadamard to controlled X's and I measure them. And then I designate my sampler as this backend sampler V2. Okay, I'm telling it to use the simulator as opposed to real hardware. Okay, Another aspect is primitive unified blocks. These are the arguments that you'll pass to running any sampler. Now, at the simplest level is just a quantum circuit. However, in later examples, like for hybrid algorithms, we can pass parameters to this circuit, how much to rotate a qubit, that we can train on classically with, basic optimization algorithms. Anyone familiar with machine learning, think Atom or any other optimizer like that. A lot of stuff we use from, SciPy or other libraries like that. And so these primitive unified blocks are basically groups of arguments to run with. But at the most basic level, we just have to pass a circuit. So I pass this circuit to my sampler, and then you see that we have all these things coming up. So my job is sampler.run. And so that contains all the information I have from running that sampler. Now, you'll see that the job result, data, measurement, get counts. It will also have other information in there, such as what parameters did you pass. You can specify certain precision values. You can specify, your parameter blocks and things like that. All that's going to be stored in your job. So, but we just want to get the counts of how many times were bit strings measured. So we pass job result, data, measurement, get counts. All right, and that will give us those bit strings. So in this particular instance, we got 000, 536 times, and 111, 488 times. Probabilistically, we're expecting an even divide between those. But at the same time, this is still, probability. Just because you flip a coin 1,024 times doesn't mean you're going to get, 612 of each. So that's the sampler. Now, estimator, we're computing the expectation value. So if we diagonalize the matrix and take it times, our vector, what's the result that we're going to get? There's a lot of systems where we're just trying to estimate the energy of the entire system. We don't want to have these raw bit strings that we have to process. We just want a singular scalar value for the system. And so that's where estimators come in. And so a lot of this looks the same, except for the sparse Pauli op. For any estimator, we can specify how we want that value to be calculated. And so for the sparse Pauli operator, I'm saying, measure in the z-axis on each one of these things. And here we see that our pub, instead of just being a quantum circuit this time, we also have our operator. Additionally, if we were having a parameterized circuit where we're learning the best rotation values for this, we could pass the parameters. And similar to before, our result is job.result. And then we have our result 0.data, just like sampler, but now we're requesting the EVs, the expectation values. And so I have an expectation value from this circuit of this value. And I may be trying to calculate the ground state of a nitrogen molecule or whatever the case is, and I'll be iterating with, just like machine learning, to like this is loss, trying to minimize this value. So your sampler V2 is going to give you bit string distributions. How many times did each bit string get measured? Your estimator V2 is going to give you an expectation value. And I didn't show it, but you can also get the variance, just as you can, measure something several times. You do 1,024 shots, it's going to give you the mean expectation value and also provide you the standard deviation. So with sampler V2, oftentimes in these optimization landscapes, you're getting the full state sampling. How many times did each qubit get measured in each state? Whereas the estimator is giving the averages of whatever observable you passed to it. Its efficiency. Sampler V2 is in a way more efficient, that you're just going to have the number of shots per circuit, but you're going to have to apply post-processing to try to determine what the distribution of these bit strings means. Whereas with estimator V2, I only used one Pauli observable, but oftentimes we combine different Pauli observables. And so for each one of these groups, we will have to have the shots times those number of groups. So in that previous slide, I had ZZZ, but I might have IZZ, ZZI, ZIZ, ZXZ, ZYZ, any combination of the Pauli terms, X, Y, and Z, based on what I want to measure. Mitigation, Sampler V2 has more limited mitigation options that you can just specify, whereas Estimator V2 has more advanced, such as zero noise extrapolation, probabilistic error cancellation, dynamic decoupling, and things like that. How do you control precision? With Sampler V2, the only knob you have is via shots, whereas Estimator V2, you can pass a precision parameter that will dynamically adjust the shots and the measurements to try to get you the desired precision. If you only need the bit string probabilities, use Sampler V2, but if you only need a scalar value, you need to use Estimator V2. Now, I understand that a lot of this seems very abstract. It's going to make more sense as we dive into the algorithms in the coming days. All right. Now, for these basic examples, I used backend Sampler V2 and backend Estimator V2. Okay, they don't have any native mitigation, and they're for basic use in simulators. I use them a lot when I'm just trying to prototype something. Okay, but these are quick. You can prototype a circuit with them. You don't have to set up your Qiskit IBM runtime. You don't have to worry about transpilation. If you're trying to get a basic idea of how this algorithm works, or you're just prototyping a circuit, they can be very helpful to just use like this. But if you're wanting to deploy to real hardware and you want full control of everything, you're going to have to use this with the Qiskit IBM runtime operations. You'll have to specify your Qiskit runtime service. If you don't already have this set up, you would have to pass your API and your CRN to set up your runtime service. Here you see I'm saying service.leastBusy. What I'm saying here is I don't care which quantum computer you send my information to. I just want to go to the least busy one. You can also specifically set up that, hey, you want your service to be IBM Brisbane or IBM Sherbrooke. I use my Estimator V2 instead of my backend estimator here. Okay, I set up my circuit, I set up my observable, and then I use this generate preset pass manager. This is a function from the Qiskit IBM runtime. Okay, and what this does is we see this optimization level and the backend. This is going to actually transpile your circuit, that is, translate it to the actual hardware. I have some optimization here where maybe it's going to combine similar gates. I can take that all the way to optimization level 3 if I really want to make my circuit as efficient as possible. Okay, and I'm making this ISA circuit where I take my pass manager and I run that circuit. And all I'm saying here is transpile the circuit to make it as efficient as possible. And then my observable, I'm applying the layout from that actual quantum hardware. So these are the steps for, I'm not just prototyping, I'm not just playing with this. I want to make my circuit efficient. I want to deploy it to real hardware. And then I run my circuit. Now that it's my circuit and my observable are optimized for that hardware. And here, this is a pub that I'm passing. I'm passing a circuit along with my observable, and I get my result. And then I ask for my EVs, and I can check for metadata and things like that. So the backend sampler, the backend estimator, they're good for quick prototyping. They don't have the mitigation options, and they're not ready for transpilation to real hardware. If you're wanting to transpile to real hardware, you're going to use the plain Estimator V2 or the Sampler V2, and then you will have to convert your circuit with the pass manager to transpile it to the appropriate form for that actual hardware. A couple things. So the run method. All right. You're going to run it with your pubs. That's the combination of, for like sampler, it'll just be your circuit along with any parameters, those learnable numbers that we're going to apply how far to rotate a circuit or how far to rotate a gate. For estimator, you're going to have your circuit as well as observables. So what measurements you want to apply. and you can also pass parameters. You can specify the number of shots you want, and with an estimator, you can also specify the precision. What this does is this is how you're controlling how precise your measurement is. With none, it's going to use the default values. All right. It's going to return a primitive job. Okay. That job contains all the information about your run. It's really important to know if you're trying to reference a previous job, what hardware this ran on, what the parameter values were, how many shots there were, and all of these things. So this job stores all that, and then its primitive result, that job.result, that is what contains your things like the counts, or get in counts, and for your estimator will be your expectation values, as well as the standard deviation. Now, in these examples, I've just shown with one pub result, or one pub being passed, but you can group these pubs in a list to send as a batch to the quantum hardware for it to run all of those. So once again, sampler is going to give you your probability distributions on how often each bit string was measured from your quantum circuit. It's going to require you to post-process to evaluate what this means. Your estimator is going to give you a single scalar term back, your expectation value. It requires much less post-processing, but it's one scalar value versus a collection of bit strings. Oftentimes we're using these with what's called variational quantum circuits. That is that instead of saying rotate x by pi radians, we tell it to rotate x by parameter theta, and then we can update that theta with a classical optimization algorithm for us to learn the best circuit representation. This is what almost all of the leading quantum algorithms use. Whether you're talking about VQE or SQD, all these topics that we're going to cover in the days to come, these parameterized quantum circuits are what allow us to find the best representation. All right. I took the time to talk about primitives today because they're there to simplify the process if you at least have a basic understanding of what they're giving you and what they require. Both estimator and sampler are going to require you to pass them a pub, as well as parameters if you're using parameters to adaptively learn on the circuit. The difference being that estimator is also going to need the observables on in which basis do you want the measurements to do. Later today, we're going to talk about sample-based quantum diagonalization. That's one of the emerging methods that's showing a lot of promise. In the talk I attended, I think in September, we had a man from Moderna, Wade Davis, who was showing how they're using sample-based quantum diagonalization in order to understand how mRNA folds. So that's one of the algorithms we're seeing that's really allowing us to show some quantum advantage. We're also going to be talking about some of the utility scale quantum algorithms in days to come, and many of those use these parameterized quantum circuits. So by us understanding these primitives and that samplers giving us the raw bit strings that are quasi-probability distributions, the estimator is just giving us those scalar values. Understanding how to set them up and what the results give us is going to make covering these algorithms later much, much easier. So that's my presentation on the primitives. Let's do questions and answers. Does anybody have any questions? Yeah, it's in many ways it's one of the least exciting presentations of the Qiskit Fall Fest that we've done so far. But just that basic understanding, and I know it's a quick and high-level overview, but we've seen these terms and we're going to keep touching on them and refining our understanding of them as we move forward. All right. Since I don't really see any questions happening, today's a Discord day. We don't have a presentation on, state of the industry or anything like that, or, Qiskit advocates or anything like that. But I'm going to be hanging out on Discord all day while I do other research, and then I'll be back at 2 o'clock to talk about sample-based quantum diagonalization and some of the interesting problems that's being used to solve. All right, everyone. Thank you very much. I'm here. Please reach out with any questions. Oh, we got a couple questions coming in. I'll hang out. Oh, we're getting thank yous. Cool. Guys, I'll be here on Discord. Please reach out with any questions that you have, any issues that you're running into, and I'll see y'all at 2.